I think the ideas of stretching are probably the most difficult when it comes to transformation of functions, and you have got to understand quite well what is going on here. Now, we can stretch in two ways, in the same way with all the other things. We can stretch parallel to the x-axis and we can stretch parallel to the y-axis. So we'll start off with, this time, with parallel, I don't need that as well, parallel to the y-axis. Now, it's not easy to demonstrate this convincingly. You just have to think a little bit. We go to our old friend y equals x squared, but this doesn't turn out to be terribly useful. So if I were to, so we'll start with x squared. Now we'll look at 3 times f of x. Now 3 times f of x is of course 3x squared. Now if this is x squared, what will 3x squared look like? Well, it looks like this. If you've got a graphics calculator handy, it's worth sort of just looking at this, or a computer screen to just plot it, but that's 3x squared. Now the question is, what has happened to that graph? And of course the temptation is to say, it's done that. It's squashed in, because that's what it looks like. Well, fair enough. But it's also possible to argue that it's actually all gone up like that. And so we have the idea of stretching. Now, you'll notice, of course, that this point here hasn't gone anywhere. It stayed there. And we say that this point is invariant. The word invariant means it doesn't move. And so the graph has been stretched upwards, and as it's been stretched, it's got thinner. So if you remember, it's sort of trying to imagine this drawn on a sheet of rubber, and you're pulling the sheet of rubber up, but this line here is glued fixed. And so everything appears to come inwards, but it's actually being drawn upwards. And let's just try and emphasize this a little bit more, because if I had started with function x equals x squared minus 2, and then looked at 3 function x, I would get 3x squared minus 6. So this time I'm starting with this. If you were to plot that, it does this. Like that. Minus 6, minus 2. Now look at the stretching idea. And we can look at this whole idea of invariant. So both of those points have stayed there. And in fact, not only is that point invariant, the whole line is invariant. And what we're actually doing, imagine it all drawn on a sheet of rubber again, and we're actually pulling it out like this. Okay, so a stretch is not quite what you think it is. It's not just everything stretching up. It's everything above the x-axis stretching up and everything below the x-axis stretching down. So the whole lot is being opened out like that. And you must understand that. Otherwise you won't really be able to grasp these sort of quite sophisticated ideas of curve sketching which you're required to develop and understand later on. So our first rule then to do with sketching, if you like, is that let's put k for want of a better letter. If I multiply a function by k, this is a stretch times k parallel to the y-axis. Okay, so we've looked at parallel to the y-axis. Now let's look at parallel to the x-axis. Make that look a little bit like 2, it's like an infinity sign. To the x-axis. Okay, this is the tricky one to get across, really. I'll risk the y equals x squared, but you may think it's a bit of a fiddle. So we start with our old friend then, and this time I'm going to ask you to look at function 2x. Now what does function 2x mean? Well, it means replace x with 2x. So in other words, it's going to be 2x all squared, which is 4x squared. And if I ask you to draw that, it looks a bit like that. And of course, you're going to look at that and say, oh, he's going to try and convince us now that this isn't stretching up, which is what we had to think of it as in the previous example. And you're right, I am going to try and convince you that, because I'm also going to say that we could think about the curve moving like that. In other words, squashed inwards. Now, this is why the graph of x squared is not a particularly good example. And if we were to say try it with, we go for x cubed minus x. And if I asked you to draw that, it would be a cubic that does that. Then if we said, okay, what's function 2x for this one? Then I'd be looking at 2x cubed minus 2x, which is 8x cubed minus 2x. And if you then had to sketch that, you would find it does, that's not very well drawn there, and that's not very well drawn there. So ignore my little mistakes there. So this is meant to be as low down as that, and this is as high up as that. Now when you draw that one, you can see it's gone like that. Here, it is not convincing that it's gone in. It could have been pulled up. Now, of course, once we start to look at this in even more detail, then you might want to look at more than one way of producing the same effect. But at this stage, let's just try and keep it as simple as possible. So function 2x appears to squash it. Now, this one, it's not clear how much it squashes. If you look at this one, and if you put some numbers on, this is 1, this is minus 1. And if you drew it accurately, you'd find this was a half, and this was minus a half. So therefore, it appears to have shrunk. In fact, it appears to have halved it. Just keep an eye on that. With function 2x, it's halved it. Now with the sort of technology we've got available to us here, you're going to have to take my word for the next bit. If I said what's function 1/3 x, then based on this one, so I want to use that equation and not this one, I would find 1/3 x cubed is x cubed over 27 minus x over 3. What does that look like? I would find it sort of does, oh dear, not my day, that's meant to go through there. Well, let's see if we can get the next bit of it right anyway. Okay. So 1/3 x, it's stretched it out. And that's 3, and that's minus 3. If you do it with our old friend x squared and do function 1/3 x, you find that it does that. And so here we have another one of these classic anomalies with the function rules, that function kx is a stretch not times k, but times 1 over k. Let's put it in a box, parallel to the x-axis. And you might say, well, why call that a stretch when it's actually a shrink? Well, that's just the convention. So we refer to it as a fractional stretch, if you like. So remember that if there's a number inside the bracket in front of x, if it's greater than 1, then it will shrink. If it's less than 1, it stretches. And again, you can see this is invariant. The y-axis this time, so it's pulled both ways. Okay, it's not pulled like that. It's not like pulling a curtain along. It's almost like opening the curtains or closing the curtains. Okay, so some really tricky ideas here, and in the next lesson we'll try and look at some examples where we put all of these function rules together, and hopefully you'll find it a little bit more clear than I suspect at the moment. You're just sort of worrying a little bit about how this works. So, and sorry about these diagrams here, but I think they're clear enough when you look at them.
Okay, Mary, so let's have a look at this one. So solve x plus 2x equals 12. So what do you think you do first?
Okay, well, I want x on its own, so I would put x equals 12 minus 2x.
Okay, so a lot of the time we want to get x by itself, but what we want to do first is get all of these x's together. So can you see anything we can do with this? Get all these together in one place.
Oh, okay, it's 3x, isn't it?
Yeah,
so
absolutely.
3x equals 12. Oh, and so x equals 4.
Brilliant, spot on, well done.